Alright, this is another planetary problem, and what's nice about planetary problems is there's only one force involved. You get the sun, you get the planet, in this case Neptune, and the only force on the planet is, again, the force of gravity from the sun. So that's nice because it makes the problem a lot easier. So we're trying to find the speed of Neptune this time. So once again, we can write down the force of gravity between Neptune and the sun is big G times mass of the sun, object 1, times mass of Neptune, object 2, over the distance between them squared. And then we say, okay, so where does velocity come into this equation? Well, we might think that, all right, this orbit that Neptune is in going around is a circular orbit. And so in order to get this, there must be a centripetal force on Neptune. And if we remember, the formula for centripetal force is mv squared over r. Now we say m of what? Is it mass of the sun or is it mass of Neptune? Well, Neptune is the one going in the circle, so it's the mass of Neptune. So mv, again it's Neptune, velocity of Neptune, v squared over r. So this is the formula for the gravitational force, and this is the formula for the centripetal force. And it just so happens, because the centripetal force is pointing to the center, so is the gravitational force, and there are no other forces, they're exactly the same. So we can say that the gravitational force equals the centripetal force. So we can set these expressions on the right equal to each other. So we can say that G ms times mn over r squared equals mn vn squared over r. And then we look at this and we see some terms cancel. So the mass of Neptune is on both sides, that cancels. And then r cancels here, and so the r squared cancels and becomes just r. And so what's left after all that canceling is vn squared equals big G times ms over r. And we're trying to find the orbital speed of Neptune, meaning vn. So we're practically there. Now we just take the square root of both sides, and that will cancel the squared term. So vn, the velocity of Neptune, is the square root of g times ms over r. And again, this will be the orbital speed of any planet, and so this equation will always work, but the goal is not to memorize this. Memorizing this doesn't really prove you know anything. If you have this equation, which oftentimes will be given, in this equation, the key thing is being able to set those equal to each other and do the cancellation. Realizing that, hey, if this planet's going in a circle, it must have a centripetal force. That's the formula for it. What is causing that centripetal force? Oh, it's Fg, and realizing they're equal to cancel and solve this. So there's a little bit of algebra, but it's not over the top. You know, for the most part, after the cancellation, we practically have what we want. Now it's just a matter of plugging in. So Vn, we're going to plug in for this. It's going to be the square root of g, so 6.67 times 10 to the negative 11 times mass of the sun, 1.99 times 10 to the 30th, over the radius, 4.5 times 10 to the 12th. Once again, we did not need to know the mass of Neptune in this problem. And we have to be careful, because sometimes we might actually be provided this, and if we were provided that, we need to be really careful not to use it. We've got to be very careful to think what masses are used. Anyway, so I'm just simplifying this expression now, and I will get my answer. And my answer is 5,431 meters per second. And I might even round that, just significant figures, to 5,430. But in any case, that is the orbital speed of Neptune around the sun. So it's about 11 or 12,000 miles per hour if we're thinking in those terms. So anyway, but that's it. The hard work is done before you do any numbers. It's all done with the algebra. And it's something that just practice. Make sure you can do this. Make sure you know how to derive this equation. And then go from there. So until next time, I am Derek Genova. Have a delightful day.